Alright, hello everyone. This is for day 23 of Advent of Code, and today we're going hiking. So what we give them as an input is this grid, and there is a few paths, and we want to go from the top all the way to the bottom, and we want to have the nicest path possible and the longest path possible. So we want to hike as long as possible, but we never want to reach the same position, be in the same position twice. So an additional constraint for part one, we also have these directions, and at its direction positions, we can only go in a particular direction. So I think it's icy slopes, and we're not allowed to go any other direction than what is given. And with this constraint, we want to know what's the longest path from the top to the bottom. Okay, so how can we do that in code? So first, we of course need to represent positions again in this puzzle. So we have an x and y coordinate, and we also make it a data class, and we set frozen to true. So this way, it automatically generates a hash function for us. We also want to add two positions, which is just by adding the coordinates. And then we have four directions in our puzzle or in our input, and we also represent them by their position vectors. Then for the first, we represent the grid as a dictionary from a position to a string. And the first thing we do is we pass the input to get this particular grid by just enumerating for the lines and enumerating for each line to get the coordinates and then filling this characters dictionary. Then we want to convert this representation into a graph where we map each position to a list of potential next positions. So that's what we do in this function. And for this, we just go through all the characters. If the characters is a dot, so it's a path, then the next position we just find by adding all the directions to the current position. But we also need to check if this new position then is within the keys of the dictionary, so it's a position in the grid, and it's not equal to the number sign, which means we cannot walk on it. Otherwise, if it's this number symbol, we continue, we don't even add it to our graph. And finally, if it's a direction, then we know that the next direction is forced. So the only possible next position will be the current position plus this direction given by the character. All right, so that will give us this dictionary of next positions that maps each position to a potential next. And then what we want to do is find the longest path from a particular start position to a goal position, giving this dictionary. And we hope that the graph with these constraints that at some positions we need to go in a particular direction, there is no cycle. So first we try to solve the problem assuming there's no cycle, and it will be much easier and much quicker than if there's cycles and we can go around. Okay, so for that we have this dictionary, longest path to a particular position. The longest path to the start is of length 0, essentially, and then we always give a queue, and we'll have tuples of current position and the previous position, so we can make sure that we never go back. And for the start, there's not really a previous position, so we just add the start. And then while we have elements in the queue, what we do is we take the first tuple from the queue. So the first will be the shortest current path, and then we first check if we already did 10,000 steps. This means there's probably a cycle somewhere, and we raise a value error. Otherwise, we hope that there's no cycle, so then we just, for each particular of these tuples with a current and a previous position, we consider all the next positions. If the next position is equal to the previous, that's not allowed. We cannot enter a particular node twice, so we continue. And then we set the longest path to this next position is one more than the longest path to the current position. And this might already be defined, but since the queue is essentially ordered by the path length, we know that we found a longer path to this next position. And so we always can do this safely. And then we just queue up each of the neighbors. So we have the next position as the new current and the current as the new previous. And then we do this until eventually the queue is empty. And if this is the case, then we return the longest path to the goal position. Okay, so with that we can solve the problem. So we first need to find our starting position. So we just index the first and the last line and find the single position that's walkable. And then we parse the input lines to this character grid. Then we get the neighbor's graph, and then we find the longest path in this, given this neighbor's positions graph. Okay, we should probably run it on the test input, and with a bit of luck, that looks good. So we can also run it on the real input, and it also gives us the correct solution quickly. For part 2, it's a much harder problem. So it turns out these directions were not mandatory, and we can also walk in the other direction. So then it's a graph with cycles, and it's just an inherently hard problem. Okay, so how can we solve it anyway? So first, get neighbors graph passing is a bit different. So now we just care whether the character is this number symbol or not, and we get this new graph correspondingly. And then we want to simplify the graph to make our program a little bit more efficient. So previously we had a graph was the dictionary from a position, the list of position. This time we have graphs with a distance, so with a dictionary from a position to a list of tuples, a position, and the distance, how far this position is away. So some weighted graph essentially. And then what we do is we simplify the graph we got before. So for this, we just go through each of the vertices in the graph and the neighbors. So for each position and each the list of neighbors, we first check if there's exactly 2 neighbors, then it's a bit of a boring position. So we know when we come in from a certain direction, we need to leave from the other. So there's no choice to be made at this position. So we won't include it in a simplified graph. Otherwise, we will include it in a simplified graph. And for a particular position, we go through all the neighbors. And then for each neighbor, we get the next intersection in that direction of the neighbor. And then the new neighbor of this current position will be the next intersection, and the distance will be the distance to the next intersection. And how can we get this next intersection? So it returns either the next intersection or the next dead end. So we first start with a distance of 1, and then we have this while loop while the length of the current position is equal to 2. So while it's one of those nodes where we know when we come in from one direction, we need to leave the other. And for this, we just go through all the next positions of the current positions. If the next position is equal to the previous, we cannot step back, so we continue. Otherwise, we just update the previous, the current, and we add 1 to the distance. And we go through this while loop until we find the node that has either 1 or 3 or more neighbors. And then we return this this current, which will be the intersection or the dead end, and the distance to it. And then with this, we get a simplified graph, or we can fill our simplified graph, which will have much less vertices than the previous one. Okay, and with this, then we can try to solve the problem. So we'll have this exception, which no path to goal possible, which will be useful for the problem. And then we want to find the longest path from the current position to the goal position, taking into account a set of visited positions. And in order to do that, we first add the current to the set of visited positions. And then we check if the current position is the goal position. We're already there, we return 0. Otherwise, we consider all our next options, which will be its position and its tuple of position and distance if the position is not yet visited. And then if we have 0 next options, that's not good, then we erase the no path to goal possible exception. If there's exactly one position, one next option, there's no decision to be made, so we just find the longest path from the next position and add the distance to the next position to it, and that will be the new longest path from our current position. Otherwise, we need to go through all options, and for each option we'll copy this set of visited positions, and then for each option we try to find the longest path from this next position. And if this function raises a no path to goal possible error, we just continue. Otherwise, we add the path length we found. We take the path length we found, we add the distance and add it to a list of path lengths. And then after we went through all the options, we check if the length of the list of path length is equal to 0. That means we raised no path to goal possible exception in each of the options. Then we again raise a no path to goal possible exception. Otherwise, the longest path length from our current position will be equal to the maximum of all those path lengths, and we return that value. Okay, so this function allows us to find this longest path from the current position to the goal, consider taking a set of visited positions into account. So that's what we only need to solve the problem. So we again find the start and the goal position, and then we parse this input to get the character dictionary. Then we convert that into a neighbor graph. Then we simplify that graph to get this simplified versions with much less neighbors and much less nodes. and much less positions. And finally, we apply this find longest path to find the longest path from the start to the goal. Okay, we should probably check it on the test input. That looks good. It also runs on the real input. It does take a few minutes, but at least it gives us the right solution at some point. But yeah, there's probably a few things we can do more efficient, such as maybe representing this set of visited positions by a Boolean array or something like that. All right, I hope you enjoyed today's puzzle. Best of luck in the future and see you around.